It's sometimes kind of hard to be a marine biologist and an oceanographer. When you step out into the oceans and start looking, we've got a lot of problems. And sometimes the profession is looked at as one of the more depressing professions to take up. But I'm not going to go there tonight. I want to share with you tonight the things that make me feel delighted to be able to go out in the ocean, the things that I feel should lift up the soul and inspire us to think more about what it is we're doing with the oceans and how we can do better. So what I'd like to be able to do is talk about deep ocean exploration, and most of what I'm going to talk about is somewhat related to research that's gone on in my lab or with my colleagues, and most of it will focus on the very deep ocean, and part of the theme going through it is how new technology developments have taken us forward to be able to explore in more detail or do things a little bit differently. This is a photograph of our beloved Strait of Georgia, looking down from above. And what we see is the sun reflecting off a surface, which is part of what our problem is. Light reflects off the surface of the ocean, we can't see in it. The human species is a very visual animal, and we like to be able to look at things. So out of sight, out of mind, we don't know what's going on inside, so we don't tend to pay attention to it. It's a very difficult world for us to get into. But there's always been that desire to get in, and starting in the early part of last century, such as William Beebe here in the bathyscaphe that went down to 1,000 meters depth, suspended on a cable from a ship, first entry into the deep ocean, and that taken forward by people like Jacques-Yves Cousteau, who was dedicated to filming to be able to share with the public what was under the oceans. And I grew up as a child looking at Cousteau's books and movies. This particular vessel, he was able to fly free of that cable and to be able to use thrusters to move around. So what we want to do today is get down through the surface, but be able to get down quite deep. Now, to do these expeditions, we need a vessel to get out there. And over the years, we've used many different vessels from many nations, such as this one. This is operated out of University of Washington. The Thomas G. Thompson, typical big A-frame on the back to be able to lift our submersibles over into the ocean, and it's a global class vessel, so it can travel a long way. And on board our ship, we're going to take a remotely operated vehicle. We've done a fair bit of work in manned submersibles, and I'll tell you there's nothing like being on the bottom of the ocean yourself. Wonderful. But to be honest, there's some limitations in that. There's just two of you down there, and you cannot share it. The thing that I love about remotely operated vehicles is that there's a whole group in that control van. You've got people from all disciplines, all trying to work out what's going on, and you're doing that development as a team. So for the first dive, we're going to launch Ropos, and we're going to start off a little bit shallow, and we're going to go down to the seafloor. So off we go. So I just want you to remember that it is dark down below 200 meters. And so that all the images that you're going to see are taken with lights. So to be able to see, we've got to take our lights with us. And exploring the seafloor is a little bit like going through the Rocky Mountains with a flashlight and trying to figure out and put it all together and figure out what the whole seafloor looks like. So let's turn some lights on. And this particular image is taken at 2,000 meters, about 400 kilometers offshore. And I have to say, just about everywhere I've been on the seafloor, there is the mark of mankind there somewhere. This particular piece of paper was a memo from the U.S. The Postal Service, here you can see, the U.S. Ministry of the Environment. We sent a picture back to the person who sent the memo. So the first place we're going to start is at the top end of British Columbia, right on the Alaska border up here. And we're going up here with the Coast Guard ship Tully. And this is part of a program working with DFO And as a matter of fact, I'm going to talk about a little bit of research being conducted by Charisse Dupree, who's sitting over here. And she's doing work with the remotely operated vehicle to develop techniques for quantitative mapping and how is it we can do, instead of just gee whiz pictures, how can we really create replicable science and quantitative methods on the seafloor. And then the particular question is addressing fish and corals and sponge relationships. So if we look at a map of Learmonth Bank here, it's about 150 meters down on the surface, and there's a big seafloor around here which is a great fishing ground, some of the best fishing in British Columbia, and the area around the southern area of the bank is quite heavily trawled, not trawled in the northern part. So with this kind of imagery, really good imagery from the submersible, HD cameras have only just become available in the last couple of years. And most of my images, you will see a couple of dots on them, laser dots. Most of the scales are 10 centimeters apart. And this particular study is looking at the bumpiness of the seafloor and how the animals respond to that bumpiness. Here, this image, we've probably got a coral that's been broken by a trawl net, and certainly evidence here, a trawl net caught up on the bottom. The corals in our waters are absolutely spectacular. This is the red tree coral, and usually when you see them, they can grow up to about 2 meters in height, and they usually have somebody associated with them. There's a couple of fish down here, a little octopus, a little crab. So here we are going across the bottom, a couple of thorny head fish here, and we're looking at the bottom. You'll see boulders in which the boulders create a habitat for animals and looking at how the roughness then creates a surface for animals to settle on. That's a hagfish. The rockfish are often taken along by the currents. They like to, they have to spend energy to keep in one place. This is a big mouth sculpin with a beautiful face on him. And here we're coming into a coral that's sitting on a large boulder, and you can see a couple of fish that are tucked into this coral. And a little close-up on one of these, okay, got to get it right, short raker. And a halibut swimming in here, settling down. Quite a lot of halibut up in this area, good fishing ground. So this study is working with DFO to create some rigorous techniques. The particular study, in a nutshell, showed that rockfish really like to be tucked into sponges and corals, whereas the thorny head, a related group, doesn't really care at all. They're scattered out on the seafloor and anchoring themselves on the seafloor with their pectoral fins. This is a program that's part of the Canadian Healthy Oceans Network that Dr. Driver mentioned, and Paul is the director of this network out of Memorial University. And so this is one of a whole bunch of different projects as part of CONI that are scattered across the country in all 3 oceans. So now we're going to go on another CONI-sponsored project, but now we're going down to the Juan de Fuca Ridge, about 200 kilometers off the southern end of British Columbia. And here's the Juan de Fuca Ridge is a spreading ridge. It's a place where new Earth's crust is being created, and the Juan de Fuca plate is moving eastward and subducting under Vancouver Island, creating our earthquake country here. And with that magma rising up, very often there's magmatic eruptions offshore. For instance, this lava was created about 4 months before we got out there to photograph it. And associated with that heat source, we often find hydrothermal vents as well. And hot vents are formed as seawater leaks down into the crust. Is really leaky, so seawater gets underneath very, very easily. And as it goes down, loses its oxygen, it starts to dissolve metals and minerals from the surrounding rock into it. The hydrogen sulfide builds up. The water goes deeper, it gets hotter and hotter. And that buoyant, really hot water needs to get out. And if it can find a straight conduit, it comes directly out, blasting out as a jet and forming what's called black smokers. If the water is somewhat diluted by other circulation, it'll come wafting out as warmer water, replete with lots of hydrogen sulfide. And the chemistry of this water is such that there are bacteria that can use the chemical energy of chemical reactions and get that energy to fix carbon dioxide in a manner very similar to plants. So it's an analogy to photosynthesis. And that water coming out forms black smokers, such as here, where we've got chimneys forming, and that black smoke, when that hot water hits the surrounding water, which is about 2 degrees centigrade, here at 2,200 meters in depth, it instantly precipitates its load of minerals and metals, and it bonds to form little particulates of sulfide. So that's where the smoke forms, and it also makes these big chimneys. And here you see it's surrounded by animals who are feeding on the bacteria in the water. So I'm going to show you a little movie clip now taken from the Endeavour segment in the north end of Juan de Fuca Ridge. And this is the first time a marine protected area was declared on a hydrothermal vent environment in the world, basically saying, hey, these environments really are special. So we're going to start out here with diving down a deep sea morid. And behind here we see basalts. Basalt is a very common deep water rock. These are pretty old basalts, and it's got a dusting of sediments on the surface. A deep sea skate here. Here's our laser 10 centimeter scale here.